Hello, here's Jeffrey Fox again. It's the Big Data Applications and Analytics course, part of Data Science curriculum. We're on lesson 3 of the first unit in the sports informatics or sports analytics section. And we're going to deal with a specific issue in sabermetrics, namely the concept of wins above replacement, which is a nice example of how a rather complex, empirical, semi-empirical, I should say, because it's based on baseball wisdom, formula allows you to make predictions which are non-trivial. So we define wins above replacement. There are many ways of calculating because it's defined intuitively as the best way of calculating the number of wins, which is 10 times the number of runs a given player produces. We give some examples of real people. We compare different methods. We have a little aside on statistics about the coefficient of determination. We look at some fancy sabermetrics example I found in a paper, and then we end up with a summary of what we've learned so far. So that's lesson 3, wins above replacement. Here we are, wins above replacement. And sometimes it's warp, which is actually, I prefer warp to war. So that's a wins above replacement, where replacement is really replacement player. So here are lots of little references about it. It's described, I say most of these sabermetrics, there's lots of good material on the web. So the idea is there's a concept which we'll just describe a little bit more later on of a replacement player. The replacement player is the player you would use if you have essentially no money to spend. Sometimes you might consider them a journeyman player. And you need to know how many extra wins. So he's below an average player. An average player is meant to give you a positive number of wins above a replacement player. So it's meant to tell you, and it's linear in the time that you sit there playing baseball, how many wins you create above the number a replacement player might create. And it's a pretty sophisticated statistics, which it's still being developed because there are many different formulae. And the goal of it is clear. It's what I said. We need to know how many wins a given player is responsible for. And there is many different implementations. They're compared here at this website, baseballreference.com. And we have the various things. We have the baseball prospectus measure warp. We have R-WAR or B-WAR from the baseball reference site. That's the one here. And we have F-WAR from sort of probably one of the most popular websites, Fangraphs. And remember, 10 runs are equal to a win. So if you want to do runs above replacement player, you multiply by 10. So you need to decide what a replacement level player is. So a replacement layer, so it's purely, you just need to agree on how to define it. And you define it in a rather obscure fashion as contributing 20.5 fewer runs over a 600 plate appearances, which is presumably roughly a season, to the average league player. So that says that an average player over 600 plate appearances, namely per season. Now remember here, an average is paid a lot of money. These average players are very good. So 2.05 is the wins above replacement of for player in the middle of those playing professional baseball. WAR being a measure of the number of wins can be calculated for players, teams, or parts of teams, say all pitchers and all batters and things like that. And it depends clearly on the time window you do. And the player's WAR value depends on the playing time. So if you look at this definition, it means that they have if you fielded a team solely of replacement level players, which wouldn't cost you very much money, you would have 0.294 winning percentages. So you wouldn't do very well because you'd like to get 90 to 110 wins, but you would only get 47.6 wins from such a team. And this is sort of illustrate, we need to be a little respectful to these players. Here is some sort of quality of baseball in the world. And then we have replacement level for minors and majors are different. Minors is lower, and they're still out in the tail of super players. Here you have all-star players, average players, and so on. So this particular definition was changed in March of 2013 and corresponds to 1,000 wins extra for an average team summed over the two leagues. So that says the total WAR for all teams in 2013 is 1,000. Because on the average, you should have a 50% winning average. And the old definition, for instance, is used in the Wikipedia article, which is 52.7 plus 0.97 times F-WAR. So if you look at, so if you read the literature, you have to be a little careful. Some of the literature from the past is actually using the old definition, which had this 52.7, not 47.6 as the number of wins. And Cameron, who used the old definition, found that the projected record based on, here's the F-WAR, one of the WAR calculations from the Fangraphs people. And if you looked at that and compared that with the actual record of a team, then the correlation is 0.83. So that's pretty high correlation. And here we just emphasize again that we're not talking about average players. Average players are relatively rare, difficult to obtain. When your star is injured and you need to replace your star, you may or may not be able to find an average player to replace them. And these are people who are minor league free agents. They appear invites at the beginning start of the year. These are the players on the fringe of just making it into the major league. And this is again describes this Gaussian distribution of quality. Here's me back here, and it's distributed a nice Gaussian or normal distribution. But the sport of baseball is based right up here, just in the tail. All right. So you have a different you have WAR for different types of players. WAR for catchers, pitchers, and batters is different. So here we're doing position players, which are batters, at least not designated hitters, just people who field. So you have to calculate WAR from 6 components. And you use something measuring the number of runs made, which is where you might use something like WOBA, weighted on base average, which we did before. Something about running, how good you run bases, bases got by running, stolen bases, caught stealing bases, runs, and things like that. First to third on singles and things like that. All these measures of whether you got out or you did well and things like that. There's also this notorious double play. If you do double plays, then that's bad for the team. Namely, with a double play, you get out, and also one of the people on base gets out. A disaster. Then, because you're batting and fielding, and effectively you score runs as a fielder if you save a run. Then there are special adjustments for the position. Namely, a catcher gets added runs because the catcher is doing something every pitch, and so that catcher is very important. And then you compare these components to the league average, and then you go from the league average to the replacement level. So this concept of replacement level is a bit bizarre. It might have been easier to do wins above average player. is you do all these things compared to the average, and then you would do this adjustment to make it compared to a replacement level. Notice these are all messy formula, like WOBA, a pretty messy formula, and they're all based on the so-called little data, and they're like WOBA. It's this custom weighted average of 7 quantities, and we have different ways of doing more, with different ways of doing pictures and different ways of doing batters, and you just have to study it, and I'm not an expert. To just say that you just take those 100 statistics that you'll find in Wikipedia, or actually it's 115 probably, and then you find the niftiest way of using them in an effective fashion to be able to find the measure which best correlates with extra wins or extra runs. So here we now look at pitches, and you have to look at the runs allowed, which are earned runs and unearned, and the innings pitched compared to the average pitcher. And then you do again go from average to replacement. And to do this, you do it in different ways for the different measures. Fangraphs uses the thing I discussed earlier, fielding independent pitching, which was not directly ERA, but a fancy combination of the things the pitcher controls, like number of hits or number of home runs given up, where the coefficients are adjusted ingeniously to get something which averages out the ERA, but then is independent of whether that poor old pitcher is in a team which fields lousily or in a stadium that's pretty useless. I mean, for the pitcher, because it's small, or it's Denver, and so it's not so kind to the pitcher. So you have to then correct this thing here, which you correct for the opposition. Obviously, a pitcher who's playing useless opposition will do better than ones who's playing good opposition. And then you have to do the difference between the leagues. The American League is currently on the average better than the National League, and then you have to look at the difference in designated hitter and non-designated hitter. So you have to, as I mentioned, you need to correct for the poor old whether the team can defend fields well or not. And there's something called defense independent pitching, which is an alternative to FIP. It's DIPS, which has the same concept of FIP, but it's a different formula. I mentioned the ballpark effects, the Colorado effect, or the small stadium effect. And if you do big data, you can do a physics model to correct for that, but with the usual little data approach, you just do it statistically, because you know what happens in an average stadium, and you correct stadiums whether they're below or above average. And then, of course, you need for pitching some discussion of relievers versus starters. Relievers have a much better ERA, but they only pitch a few innings. And again, this is issue of the margin. If you're pitching in a close game and you're a reliever, your performance is much more valuable than if you're pitching. If you come in as a relief pitcher with the 6 runs ahead, then you have you would be shot if you didn't win that game. So it's you have an easier problem. Here are some examples of FWAR. Just the values. These are from Fangraphs. I looked them up on Fangraphs. So possibly the leading batter in 2014, Mike Trout. He had an FWAR of 7.8 in 2014 and 10.5 in 2013. Remember, 7.8 means that he probably created 78 more runs over the season than the replacement level player. So 78 is quite a big number. And he's compared to the average player who would have an FWAR of 2.05, I think we just deduced. If you look at pitchers, it's actually interesting. Pitchers have a similar value. The 2 top pitchers were Corey Kluber and I gather and Clayton Kershaw. They had 7.3 and 7.2 as their FWAR. Interesting that Clayton Kershaw was a little behind Corey in the wins above replacement measure, whereas if you look at the actual record, Kershaw's far ahead. He's the Dodgers pitcher. 21 wins, 1.77 ERA. Kluber was 18 wins and 2.4 ERA. Presumably reflects something to do with the teams they're playing for or the stadium they're playing in. If you look at the whole team, the Dodgers in 2014 had a wins above replacement of 41.8, which came roughly 2/3 from batting and 1/3 from pitching, a little over 1/3 from pitching. Red Sox had a somewhat higher wins above replacement as a team. Remember, 43.3 means they have 433 runs, more than the a team of replacement level players, and it was divided. Actually, some of them more dramatically. Obviously, the Red Sox were a better batter than pitching compared to the Dodgers because they had significantly larger batting total than the Dodgers and a lower pitching total. If we look at the whole time, and of course you're going to favor the players who've been playing the longest time. If you add over all the years, then you'll find that Babe Ruth, who was of course a very famous, he and Mickey Mantle, very famous baseball players. He had 10,616 plate appearances, and he had a Fangraph wins above replacement of 168.4, and then a much more recent player, Barry Bonds, with almost 2,000 more plate appearances, had a somewhat lower F-WAR. PA here is plate appearances. And notice that this is almost has to be done with little data because I'm allowed to calculate it for Babe Ruth, who obviously was batting and playing before any of this video stuff came along. And so this is one advantage of keeping to the clean, simple, classic data, but complicated formulae. You can then apply it over for the 140 years or whatever baseball has been played for. These next three plots we can go through reasonably quickly. It just came from an article which compared the different ways of calculating WAR. Here is the WARP from one of the baseball sites, and the R-WAR. And here is the this thing here is the linear curve. R-WAR equals WARP, and here's the actual data, which shows actually a reasonably clear different slope. Namely, when here we have when WARP is 4, R-WARP is much higher. So there's a significant differences there. Actually, slightly surprising effect, that big an effect, and they're all meant to be determined by a very reliable formula. In my opinion, these people produce a quadratic fit, which I think is a mistake. I'll mention that a little later on. The R-squared I'll also discuss is the measure of the qualitative. It is not terribly good. But obviously these different approaches are correlated, but the fact that the slopes aren't the same is slightly alarming, because the slopes ought to be the same if they're reliable, because these are meant to be wins. And if the slopes are different, it's saying that R-WAR is suggesting that fewer runs are coming from the leading players and more runs coming from the non-leading players. I should say the sample of data had 85 players here, 30 super players, 30 not so placement level players, and 25 average players. Here we are again with another quadratic fit, and this one actually is a higher R-squared and is a little more satisfactory. This is Fangraphs versus R-WAR, and this is better in that the best fit is actually pretty near the linear fit, and there's a slight skew here, but not nearly as dramatic as in the previous graph. And here's the final plot. This is actually interesting. The deviation is narrow. Namely, this is not so far from the line. This distance here is small, and that's why the R-squared is big for the fit. However, it's again for the same reason. WARP underestimates for the high end the number of wins above replacement players. So there's a very significant difference between warp and the other two measures in terms of the contribution to the performance of a team of the leading player. This, I suspect, if you were unbiased and were given enough money and enough access to data, you could decide which of these was better, because I would think that you would get pretty different answers if you looked at the right measure, if you compared analyzing performance of the actual performance of teams versus that predicted from the wins above replacement. So that's sort of interesting. We now come to some remarks on this. As I said, they show a linear slope 1 curve, the best fit. They also show this, what I think is a catastrophe. Wow, I didn't know I couldn't pronounce catastrophe. Of a quadratic fit. The reason why a quadratic fit is obviously, in my opinion, wrong thing to do is these various measures of war are meant to be roughly linear. They may not be exactly linear, but they're measuring wins, and you can't have one giving wins that are quadratically dependent on the other one, because that means that as you just extend the graph above the place you plotted it or below at either end, that quadratic term is going to get more and more important, and you're going to get drastically different answers. So I think you have to use. So I would consider quadratic fits as a very unwise thing to do. There are other formulae. If you read the how to do fits, you'll find other ways of doing it, which I'm sure are better ways to do it. I strongly recommend against quadratic fits. In general, they're pretty difficult. People always, if you read your book about how to do modeling, par laws are the very bad things to use because they wobble up and down. They go up and down. 10th order fit. It just wiggles around to fit all the data, and that gives nonsense as soon as it gets outside the region of this fit. So it can produce formally a good fit, but it's meaningless. So R squared is something was meant to be near 1. We have a couple of slides here on R squared, which you can look up in, again, Wikipedia, the coefficient of determination. And it's a very important thing to calculate whenever you do fits. You're never going to get a perfect fit because you're bound to have some scatter. And remember, actually, one of them, the R war against F war, the scatter was actually pretty small. There was a slight deviation from linearity, but not very big. And actually, a linear fit wouldn't do too bad at all. So the normal way you measure goodness of fit is the residual. If you have some measurements yi, which say maybe F war, and you have some xi's, which are warp, and you want to measure the quality of a model, which expresses F war in terms of warp, so it's a quadratic model, you just take the measured value of the say F war, here's the model based on warp, you take the difference, square it, and then you sum it over n. That's a classic least squares measure of the residual. And this residual is 0 if the fit is perfect. Then the modeling equals the measured value. And normally, actually, if you did least squares, you would divide this by an error. In this type of example here, we don't have an error. At least not one we think we can do. Although, if we actually worked on it, we probably might be able to get an error. And then you'll get chi-squared. When there's chi-squared is very important. And these things we're doing here are effectively slightly screwed up chi-squared where we've been lazy and not estimated an error. And so instead of that, we use the actual variation of the individual measurements here, which are the dependent variables here. Xi are called the independent variable. They're the warp if we're doing F war in terms of warp. And we use just the jitter in the measure in the dependent variables to determine to normalize the error, because a chi-squared has to have an error variation. And so we look at this thing here, which is the y variation, which is just this is the normal definition of variance. And then you take the residual, which is the sum of I equals 1 to n of yi minus the model, all squared, divided by the y variation, which is sort of the trivial model equal to 0. And 1 minus that is r squared, the coefficient of determination. Obviously, if the residual is 0, r squared is 1. We were getting residuals sort of like 0.8 or 0.9, and that's obviously pretty reasonable. And actually, in the case where I prefer to use, namely a linear model, r squared is just the square of the correlation between the x's and the y's. And again, correlation, if perfect, is 1, then r squared equals 1, because r squared is the square of the correlation. So this is just a little bit of a side on statistics illustrated for this particular concept. Here we have some discussion of a paper I found on the web, came from the Sloan Sports Conference in 2014, the last one, February 2014. And this is a paper by people from MIT. MIT seems to do a lot of work in this area. There were several papers from MIT. And the goal is to try to get a predictor for when to swap out a picture and put in a relief picture. And again, it's an example of using little data, but instead of using these formula, it actually uses machine learning. It does do a regression formula, which is linear in feature vectors. And it has the usual concept of machine learning. You take part of the data, train it to get the coefficients, and then you test on the rest. And like in all of these things, you must have the feature vector, which is what you think it's going to. This is where you put in your expertise. You decide what are going to be the features which we use to make the predictor. Then we say, all right, the real answer is some linear dependence on these feature vectors. we'll decide on what those what the linear formula is. And here you have all sorts of statistics on the current games, previous innings of this game, and also some features coming from previous games, such as ERC and slug and things like that. And then the results are compared to what managers do. This is meant to be the correlation of these ones here, the correlation of the manager with actually what happened, namely whether the manager swapped the picture at the right time or not. The manager's got sort of a 75% accuracy, and this thing is more like an 80% accuracy, so it improved over managers. So you can replace the manager by a regression formula. But of course, the manager does other things other than switching out relief pitchers. And that's the final slide of this section, a summary of little data sabermetrics. And as I point out, they're modest volumes of data. I keep emphasizing this, but it's hugely high quality data. It's much higher quality than many data people look at. We have these interesting example of magic coefficients in FIP and WOBA. And also the rather complex empirical Bohr formulas. And these coefficients don't come from theory. What comes from theory are the feature vectors, which we discussed in the last slide. And the feature vectors are the things you add up, say in WOBA. Those are the features you decide are important to put into that formula. Then you let the data determine which numbers give the best answer, say in a particular year of a particular team. You can obviously determine these formulae in many different ways and different averaging. So notice that classic sabermetrics illustrates a key feature of big data, namely the data, not the model that determines the answer. What the person puts in are the features. They put in the variables the model ought to depend on. The data finds the answer. And that's why you have to be a baseball expert to work in this field. And there is, I note, a nice edX course in this area. And it basically focuses on what I call here little data sabermetrics, the stuff we just discussed. And it has modules on using SQL and R to do the calculations that you might want to do in this area. All right, sabermetrics, that's it. We'll go on to more well, at least little data sabermetrics, that's it. We'll now go on to more complex discussions depending on the video data. Thank you very much. This is Geoffrey Fox signing out at the end of this first unit on sports analytics, search informatics. Thank you.